What do you think is the biggest danger for an astronaut traveling to Mars? You might think radiation from the sun. You might think the vacuum of space itself. You might even think about the psychological toll of being isolated for months. But here's the thing. Before the astronaut even gets near Mars, before they even leave the Earth-Moon system, they have to pass through something we discovered completely by accident. Back in 1958, the United States launched its first satellite, Explorer 1. It was a pretty basic thing, compared to what we have today. But on board, there was one clever instrument, a Geiger counter. A Geiger counter is just a tube that clicks when radiation passes through it. It's so simple. They wanted to measure cosmic rays, these high-energy particles that come from space and bombard our upper atmosphere all the time. Pretty straightforward, right? Now, James Van Allen, the physicist who designed this instrument, expected to find cosmic rays. He'd studied them from the ground, from balloons at high altitude. He had a pretty good idea what to expect. But then something strange happened. When Explorer 1 reached very high altitudes, thousands of miles up, the Geiger counter started acting peculiar. It wasn't detecting more cosmic rays, which you might expect the higher you go. No, it was detecting nothing. Absolutely nothing. Like someone had turned off the cosmic rays completely. Now, you have to understand how surprising this was. Here's Van Allen. He's looking at the data coming back from this satellite, and the instruments that worked perfectly at lower altitudes are now saying, nothing, nothing, nothing. His first thought was probably that the instruments were broken, right? But then more data came in from other tracking stations around the world. Australia, Singapore, Nigeria, they all reported the same thing. At very high altitudes, the Geiger counter recorded essentially zero cosmic rays. Well, you can imagine the puzzlement. Van Allen thought about this. It's a very interesting moment in science. You see, when data contradicts your expectations, you can't just ignore it. You can't throw it out. You have to ask, what could possibly explain this? And after careful analysis, Van Allen came to a stunning conclusion. There wasn't less radiation up there. There was much more. So much radiation, actually, that it was saturating the instrument. The Geiger counter couldn't handle it. It was like trying to count raindrops during a hurricane with a rain gauge designed for a drizzle. But here's where it gets really interesting. This radiation wasn't cosmic rays. It was something else entirely. Something that was trapped in Earth's magnetic field. Something that had been sitting right above our heads the entire time, and nobody had ever detected it before. Let me explain what he discovered. Imagine Earth sitting in space. The Earth's core is made mostly of iron, and this iron is moving. It's churning inside the planet. Moving iron generates a magnetic field, a powerful magnetic field that extends far out into space. This field is called the magnetosphere, and it's like a giant invisible shield wrapped around our planet. Now, here's the thing about charged particles, electrons, protons, particles like that. When they move through a magnetic field, they don't go straight. They curve. They spiral around the field lines like a bead sliding along a wire. The sun is constantly throwing these charged particles at us. It's called the solar wind. It's this stream of particles, mostly electrons and protons, just pouring out of the sun constantly. When these particles from the sun hit Earth's magnetic field, they don't slam into the planet. The magnetic field bends them, curves them, and traps them. And not just a few. Billions and billions of particles get trapped. They start spiraling around the magnetic field lines, bouncing back and forth, trapped in a region that extends from a few hundred miles above Earth's surface all the way out to tens of thousands of miles. What Van Allen found was actually two belts of these trapped particles, two enormous, invisible donuts of radiation surrounding the planet. The scientists named them the Van Allen belts, which I think is only fair since he discovered them. Now let me paint you a picture of what these belts look like. Imagine standing here on Earth. Directly above you, starting at about 400 miles altitude, there's the inner belt. This belt extends down to lower altitudes in some places and reaches out to about 6,000 miles in others. It's made primarily of protons, heavy particles. Where do these protons come from? Well, here's an interesting detail. Cosmic rays are constantly hitting Earth's upper atmosphere. When they hit, they smash into nitrogen and oxygen nuclei, and this collision releases neutrons. Now, neutrons are electrically neutral, so the magnetic field doesn't trap them. But neutrons don't last long. In about 15 minutes, a neutron decays into a proton and an electron. And boom, The proton gets trapped by the magnetic field. So the inner belt is actually continuously fed by cosmic rays hitting the atmosphere. Then you have the outer belt. This one is a bit different. It reaches much farther out, starting at about 8,000 miles and extending to maybe 40,000 miles or more. It's made mostly of electrons, and these electrons come from the solar wind. When a solar storm happens, when the sun throws particularly energetic particles at us, the outer belt gets worse. It fills up with more particles, so the outer belt is variable. Sometimes it's worse, sometimes it's better. Now, here's the thing that makes this barrier so important for space travel. The radiation in these belts is intense. We're not talking about a little background radiation like you might get from living near a uranium mine. We're talking about particles moving at tremendous speeds, carrying enormous amounts of energy. When one of these particles slams into something, say, a human cell or a computer chip, it can do real damage. For a human, the damage is insidious because you don't feel it happening. Radiation doesn't hurt. You can't see it, you can't taste it, you can't feel it. But inside your body, these particles are ionizing atoms and molecules. They're knocking electrons loose. They're breaking chemical bonds. They're creating free radicals that can damage DNA. And if enough cells are damaged, well, you can get cancer. Or if the damage happens in your brain or bone marrow, you could get acute radiation sickness. You could die. For electronic equipment, the problem is different but equally serious. A single high-energy particle can hit a microchip, flip a bit from 0 to 1 or 1 to 0, and crash a computer system. Modern microchips are so small, so delicate, that they're incredibly vulnerable to this kind of damage. That's why NASA has to harden spacecraft electronics against radiation. They have to design them to tolerate hits. So we have this barrier, these two donuts of intense radiation surrounding the planet, and astronauts need to pass through them to get to the Moon, to Mars, to anywhere beyond Earth orbit. Now you might ask, how does anyone get past them? Is it even possible? Well, yes, it's possible, but you have to be clever about it. The first thing you understand is that the belts are not uniform. They're not equally intense everywhere. In some places, they're thinner than in others. There's even a gap between the inner and outer belt, a relatively safer zone. Also, the South Atlantic anomaly is an interesting feature. The Earth's magnetic field is slightly tilted and offset from the center of the Earth, so the inner belt dips much closer to the surface over the South Atlantic. If you have to pass through the belts, you want to avoid that region. The second thing is speed. If you're moving fast through the radiation belt, you're exposed for less time. Less time means less radiation dose. This was the key to the Apollo missions. The spacecraft flew very quickly through the thinner parts of the outer belt, avoided the inner belt entirely by going to the side of it, and by moving at high speed. The astronauts' total radiation exposure was actually quite low. Harmless, really. Apollo 8, in 1968, was the first crewed spacecraft to go through the Van Allen belts and reach the Moon. The astronauts, Jim Lovell, Frank Borman, William Anders, they flew through this region that scientists had been worried about, and they came back fine. They've lived long, healthy lives, and there's no evidence that the radiation from passing through the belts caused them any problems. The secret was the route they took and the speed they maintained. But here's where the problem becomes more acute when you think about something like a Mars mission. To get to Mars, you have to do something different. You don't just do a quick pass like the Apollo missions. You might be in space for many months. You might spend a long time beyond Earth's protective magnetosphere, exposed to galactic cosmic rays. These are the rays coming from outside our solar system, traveling at nearly the speed of light. These rays are incredibly energetic, and there's no good way to shield against them without adding enormous amounts of weight to your spacecraft. When we talk about shielding, there's this interesting problem that most people don't realize. You might think more shielding is always better. Just wrap the spacecraft in thick lead or something. But that's not quite how it works. When a very high-energy particle hits a thick shielding material, sometimes it breaks apart into secondary particles that can be even more dangerous than the original particle. It's called the fragmentation problem. A heavy nucleus moving at very high speed hits your aluminum hull. Pow! It shatters into lighter fragments, and these fragments scatter in different directions, potentially doing more damage than the original particle would have done. So the solution is more subtle. You need shielding materials with low atomic numbers, like hydrogen or helium or carbon. These materials, when hit by energetic particles, produce fewer dangerous secondary particles. Polyethylene is actually quite good. It has a lot of hydrogen in it, or water. You can use water as shielding. Some spacecraft designs have actually considered using water tanks as both a drinking water supply and radiation shielding. Clever, right? Killing two birds with one stone. But even with shielding, there's a limit. Scientists estimate that the total radiation dose an astronaut can safely accumulate is reached after about 500 days in space beyond Earth's magnetosphere. For a mission to Mars and back, you're looking at 6 months or more of travel, plus time on Mars or in Mars orbit. That's approaching or exceeding that 500-day limit. And we're still not even sure what that limit really is. There's still a lot of uncertainty about how radiation affects human health, about genetic damage, about cancer risk. These are active research areas. Now let me tell you something else interesting about these Van Allen belts. They actually do something useful for us. They shield Earth from a lot of the radiation that would otherwise reach the surface. Without the magnetosphere and these radiation belts, much more cosmic radiation would hit our atmosphere and reach the surface. Over evolutionary timescales, this would be devastating. In fact, one reason these belts are so interesting to scientists is that they might tell us something about planetary protection. If we found a planet with no magnetosphere, no radiation belts, it might be much less hospitable to life because of increased radiation. Also, the Van Allen belts are a kind of natural laboratory for studying plasma physics. This is the study of ionized gases and how they behave in electric and magnetic fields. Understanding these belts helps us understand similar phenomena happening in the Sun's atmosphere, in other planets' magnetospheres, even in distant galaxies. So the same barrier that makes space travel harder also teaches us fundamental physics. Let me tell you about a more recent discovery that really shows how much we still have to learn. In 2012, NASA launched 2 spacecraft called the Van Allen probes specifically to study these belts. These spacecraft were much more sophisticated than Explorer 1 with its simple Geiger counter. They had sensitive instruments to measure particles, waves, electric fields, magnetic fields, everything. And almost immediately after launch, the Van Allen probes discovered something surprising, a third radiation belt. Now, the belts aren't static. They change. They fluctuate. During solar storms, the outer belt swells up with more particles. During quiet times, it shrinks. But a third belt? That was new. It didn't last long. It persisted for about 4 weeks. But the fact that it appeared at all suggested that the structure of the belts is more complex than we thought. The boundaries aren't as clear-cut as we assumed. There's more dynamic behavior, more interesting physics happening. The Van Allen probes also discovered something called the impenetrable barrier. For the fastest, most energetic electrons in the outer belt, there's a sharp inner boundary. These electrons simply cannot penetrate it. They bounce back. It's like a wall. Scientists don't fully understand why this barrier exists or what maintains it. It's a genuine mystery. It might have something to do with waves in the plasma that prevent the electrons from going further in. It might be something else entirely. But it's an example of how nature still has secrets to reveal. One of the things I love about this topic is how it illustrates scientific method in action. We made a discovery by accident. We were looking for one thing, cosmic rays, and found something completely different. We've been studying these belts for 60 years, and we're still making new discoveries. We're still confused about some aspects of how they work, and that's wonderful. That means there's still much to learn. Now let's think about the future. If we're going to send humans to Mars, we need to solve this problem. The Van Allen belts are just the beginning. Once you get beyond them, you face galactic cosmic rays. And those are a much tougher problem because they're so energetic that you can't really shield against them effectively. Some concepts that have been proposed include artificial magnetic fields. If you could generate a strong enough magnetic field around your spacecraft, you could deflect charged particles just like Earth's magnetosphere deflects them. This would work for solar wind particles, but for ultra-high energy cosmic rays, you'd need absolutely enormous field strengths. It's probably not practical with current technology. Faster transit times. If you could get to Mars more quickly, say in a couple of months instead of 6 months, you'd reduce radiation exposure. This would require more powerful propulsion systems, maybe nuclear rockets or ion drives. We're working on this technology. Better understanding of radiation biology. Maybe the actual safe limits aren't as restrictive as we think. Maybe there are ways to protect the most critical systems, the brain, the reproductive organs, while accepting some radiation exposure elsewhere. We need more research, going underground or finding caves on Mars. When you land on Mars, you could establish habitats underground, where the Martian soil provides shielding from cosmic rays. This might actually be necessary. And here's something nobody talks about much. Maybe we need to accept some risk. All exploration involves risk. The Apollo astronauts accepted risk. The early explorers who crossed unknown oceans accepted risk. Perhaps some radiation exposure is simply part of the price of space exploration. That doesn't mean we should be cavalier about it. We should do everything we can to minimize it. But we shouldn't let the perfect be the enemy of the good. What's fascinating about the Van Allen belts is that they're actually more than just a barrier to space travel. They're a window into how the sun, Earth's magnetic field, and the space environment interact. Every solar storm changes the belts. Every quiet period lets them recover. The belts are in constant conversation with the larger space weather environment. And speaking of the larger picture, let me tell you something that might surprise you. The reason the Apollo moon landings happened during one of the worst periods for solar activity, a solar maximum, when the sun was throwing more particles at Earth than usual, was actually lucky, not unlucky. You see, when the sun is very active, its magnetic field is stronger. This stronger magnetic field actually shields the inner solar system from galactic cosmic rays. It's like an umbrella. So even though the solar wind and solar storms were worse during Apollo, the astronauts were actually exposed to fewer galactic cosmic rays than they would have been during a solar minimum. By chance, the political imperative to land on the moon in the 1960s actually corresponded to the best time from a cosmic ray perspective, if not from a solar activity perspective. This is the kind of beautiful, subtle thing that nature does. There are trade-offs. Nothing is simple. You can't just ask, when is it safest to go to space? Because safety from one thing means exposure to another thing. You have to think holistically about the entire radiation environment. Let me come back to the basic physics for a moment, because I want you to really understand what's happening. Remember I said that the Van Allen belts are made of particles trapped in Earth's magnetic field? Let me explain more carefully what trapped means. When a charged particle moves through a magnetic field, it experiences a force, the Lorentz force. This force is perpendicular to both the direction the particle is moving and the direction of the magnetic field. So the particle curves. If the magnetic field is uniform, the particle would just curve in a circle. But Earth's magnetic field isn't uniform. It's stronger near the poles and weaker near the equator. Now here's the clever part. The magnetic field near the poles is stronger, so particles curve more sharply there. The result is that particles spiral around the magnetic field lines in tight loops, and when they reach the strong field regions near the poles, they get reflected. They bounce back. It's like a magnetic mirror. The particle bounces back and forth between the northern and southern magnetic poles, spiraling as it goes, creating these donut-shaped regions of trapped particles. This bouncing behavior is why the belts have boundaries. A particle with a certain speed and energy might be trapped and stable in the belt region. But if you move slightly inward toward Earth, the magnetic field gets different in a way that doesn't reflect the particle anymore. It gets absorbed. Or if you move outward, the field weakens too much and particles can escape into space. So there are natural boundaries where the trapping happens and where it stops. This is actually relevant to understanding that impenetrable barrier I mentioned. The very energetic electrons in the outer belt, the fastest ones, they might be prevented from moving inward by some effect we don't fully understand. It might be related to waves in the plasma that interact with these electrons in just the right way to send them back. Or it might be something else. But it's another example of how the magnetic field creates these subtle boundaries and barriers. Now, I want to address something I think is important. When you read about the Van Allen belts online, you often see conspiracy theorists claiming that they're an impenetrable barrier that makes the Apollo moon landings impossible. How could the astronauts survive the radiation? They ask, with this tone of gotcha. But this is based on a misunderstanding of the radiation environment. The belts are intense, yes. The radiation levels are high, but they're not some kind of absolute death zone. It's a matter of dose, how much radiation you receive. You can pass through them and receive a dose that is harmful, but not immediately lethal. The Apollo astronauts did this. They spent a few hours in the high radiation regions of the belts. Their total exposure was probably less than you'd receive from a full-body CT scan. Not ideal, but not lethal. And the truth is, NASA was careful about planning these trajectories. They routed the spacecraft to go through the weakest parts of the belts. They launched when solar activity was high, which actually reduced cosmic ray exposure. They flew at high speed to minimize time in the high radiation regions. It wasn't like they just flew straight up through the middle of the inner belt. That would have been much worse. So while it's true that radiation is a real problem for space travel, the Van Allen belts aren't an absolute barrier. They're a challenge, but a manageable one if you're smart about how you approach it. Let me wrap up by thinking about what all this means for the future. We have plans to go back to the moon with Artemis. We have plans to send humans to Mars, probably sometime in the 2030s or 2040s. These missions will have to deal with the Van Allen belts again, but the solutions are well understood. You route your spacecraft carefully. You move fast. You limit the time your crew spends in the high radiation regions. Once you're beyond the belts, the next problem becomes the galactic cosmic rays. For Mars, the challenges are greater because the journey takes months. You can't just sprint through the radiation environment. You're exposed for much longer. This is where we need new technology, better shielding, faster transit, or a better understanding of what radiation doses are actually safe. All of these are areas of active research. But here's what I find remarkable. Humanity looked at this problem, said, okay, this is hard, but let's figure it out. And we're doing exactly that. The Van Allen belts are not the end of space exploration. They're just one of the puzzles we have to solve. And I think, ultimately, we will solve it. The universe is big, and it's far away, and getting there is difficult. But that's what makes it worth doing. If it were easy, it wouldn't be interesting. The fact that we have barriers to overcome, mysteries to unravel, problems to solve, that's what drives science. That's what drives exploration. So the next time someone tells you that space travel is impossible because of the Van Allen belts, you can tell them, no, it's not impossible. It's hard, yes. It's complicated, yes. But we've already done it. We know how to do it. And with more research, we'll get even better at it. That's the beauty of human ingenuity applied to a difficult problem. The barrier that stops all space travelers is real, but it's not a barrier in the sense of being impossible. It's more like a guardian at the gate. It says to us, if you want to go into the cosmos, you have to earn it. You have to understand me. You have to respect the forces at work here. And if you do, you can pass through. And that's a message I think worth heeding.